Okay, hi, I'm Alan, and today I'll be talking about learning quantum Hamiltonians at any temperature in polynomial time. This is joint work with Einish Bakshi, Ankur Moitra, and Ewan Chen. Okay, so let me begin with a high-level introduction to Hamiltonian learning. So in Hamiltonian learning, we're studying a system of many interacting particles, say n interacting particles. And these particles interact locally, but their interaction strengths are unknown. Now, these local interactions give rise to some macroscopic properties in the system. And Hamiltonian learning is the study of this inverse problem. So given a system of interacting particles at equilibrium, can we learn about the local interactions from measurements of the macroscopic properties of the system? So can we go backwards from measurements of the macroscopic properties of the system to learning about the microscopic forces driving them? Now, Hamiltonian learning is a well-studied problem. There's a extensive line of literature on it. And so it is a foundational problem in understanding quantum systems. And so while tomography for fully general systems is hard, Hamiltonian learning is the study of can we efficiently learn about physically relevant classes of quantum states. And furthermore, with recent advancements in quantum computing, Hamiltonian learning has emerged as the dominant paradigm used by physicists for verifying and benchmarking quantum devices. So the current state of affairs in Hamiltonian learning is as follows. It is that existing algorithms can solve Hamiltonian learning efficiently only at high temperatures. Unfortunately, this is exactly at odds with why Hamiltonian learning is useful for applications, and that is because interesting quantum phenomena arise only at low temperatures. So this means that in order for Hamiltonian learning to be a useful paradigm for all of these applications, we really need to understand and perform Hamiltonian learning at low temperatures. So the main question we'll seek to address in this talk is, can we solve Hamiltonian learning efficiently at low temperatures? And there's actually very limited positive results or very limited positive algorithmic results at low temperatures. And this lack of positive results has even led to conjectures that the problem of Hamiltonian learning is actually computationally hard at low temperatures. So for instance, there was a survey by Anshu and Aruna Shalom in 2023 where they conjectured that there may actually be computational barriers to solving Hamiltonian learning efficiently at low temperatures. Now, if there were such computational barriers or computational hardness, then this would be a major roadblock for Hamiltonian learning being useful for all of these applications, because it would mean that we cannot hope to efficiently or algorithmically solve this problem of Hamiltonian learning exactly when we need to solve it for interesting quantum systems. Fortunately, we show that there are no such computational barriers, and there is good reason for optimism because efficient Hamiltonian learning is possible at any temperature. So now let me begin with a bit of a more formal problem setup. So as I mentioned, we're studying a quantum many-body system, say, consisting of n particles. And so the state of each particle is described by a matrix, S of I, that's a 2x2 matrix. Now, the full state of the system is described by a 2 to the n by 2 to the n density matrix rho. Now, there are a few constructions that we need to develop to define this problem of Hamiltonian learning. So first, there's some underlying local topology of the particles. And then there are these local terms, say E sub A, that describe the local interactions between the particles. And finally, there's this notion of the local Hamiltonian, which is the linear combination of local terms describing the interactions between all of the particles. And now the problem of Hamiltonian learning will be given an unknown local Hamiltonian so for an unknown local Hamiltonian, we'll be given these copies of the Gibbs state rho, given by this e to the minus beta h over a trace of e to the minus beta h, and the task will be to learn h given these copies of the Gibbs state. Okay, so now let me formally define these constructions that I mentioned here. So first, the local topology. So we'll assume that there's some known arrangement of the particles. In particular, we'll assume that the particles are at the nodes of a constant degree graph G. And so now we'll assume that the interactions between the particles are local with respect to this graph G. And so this is a natural and physically motivated assumption because like physically particles interact more strongly with those that are spatially closed. So now our results will hold for any constant degree graph, but for simplicity in this talk, let's just consider a 2D grid. So we'll imagine that our particles are exactly at the nodes of a two-dimensional grid. Next, we'll define the notion of a local term. So a local term is describes an interaction between particles in a small neighborhood. So a local term describes a so a local term here, E, describing an interaction between S1 and S2 can be written in the following form. So E can be written as M, so a 4x4 operator on the subsystem consisting of sites S1 and S2, tensored with identity on all of the other sites. So this term E, acting on only sites S1 and S2, can be written as a tensor product of an operator on this 4x4 subsystem, tensored with identity, so a trivial interaction everywhere else. And so more formally, we say this: the port of an operator E is a set S of the following form, such that this operator E can be written as some operator M that is a non-trivial 2 to the S by 2 to the S operator acting on only the subsystem of sites in S, tensored with identity on all the other sites. And so we say that a term is k-local if its support is contained in a connected component of size k in the underlying graph. And throughout this talk, we'll treat the locality k as a constant. So for instance, in this example here, this operator E acting non-trivially only on S1 and S2 would be a 2-local operator. So now a local Hamiltonian is simply a linear combination of local terms. So formally, a k-local Hamiltonian is a 2 to the n by 2 to the n Hermitian matrix, the following form. So we have this linear combination of these local terms E sub a. So here we use the standard normalization that the coefficients lambda a are between -1 and 1. And the terms E sub a are the elements of a, let's say, canonical basis for the set of local terms. For people who know what this means, P sub k is like the Pauli basis for the set of all k-local terms. And now the interactions between the particles in our system are governed by a local Hamiltonian. So this local Hamiltonian really is the aggregate of all of the individual local interactions throughout the system. There's a linear combination of all of these local interactions added together. Okay, so now we can define the learning goal. So for a k-local Hamiltonian H, the Gibbs state at a specified inverse temperature beta is this rho is e to the minus beta h over a trace of e to the minus beta h. This is the 2 to the n by 2 to the n state. And so the physical interpretation for this is that this is the equilibrium state of the system at a specified inverse temperature beta. So in other words, if the interactions between the particles are as specified by h, then the equilibrium state of the system at this inverse temperature beta will be given by rho. Now, the problem of Hamiltonian learning is we're given measurement access to copies of the Gibbs state, and the goal is to learn the coefficients, so learn the lambda a's. So recall that the structure, so the underlying topology is known, so sort of all of the terms E sub a and this canonical basis are known. And so the only unknowns are these coefficients, the lambda a's. So the problem is to learn these coefficients. So when we say efficient, so we want efficient algorithms, and by efficient, we mean polynomial in n, where n is the number of particles. So while technically the state has dimension 2 to the n, all of the local terms are succinctly describable in time polynomial in n. And so we'll also ask for measurements and computations that can be performed in time polynomial in n. Okay, so now let's discuss some prior work on Hamiltonian learning. Really, there are two main prior works that are most relevant here. So first is this paper of Anshu, Arunachalam, Kuwahara, and Sulaimanovar in 2020. So they give an algorithm that uses polynomially many samples, but requires exponential runtime. And second, there's this work by Ha, Kothari, and Teng in 2021, and they give an algorithm that works in polynomial time for sufficiently small beta. So recall beta is inverse temperature, so small beta means high temperature. In particular, for beta less than some critical constant beta sub c, their algorithm works in polynomial time. However, this is a hard phase transition in the sense that when beta is larger than this critical beta sub c, their algorithm actually requires exponential time or does not work at all. So now the takeaway here is that previous works only give efficient algorithms in the high temperature or small beta case. And again, as I mentioned previously, this is exactly at odds with why we really care about this problem of Hamiltonian learning, because we really want to study Hamiltonian learning at low temperatures, precisely the regime where interesting quantum phenomena arise. Now, in these previous works, there are actually very fundamental barriers why they get stuck at high temperatures and why they do not work at low temperatures. So these fundamental barriers, or these barriers are that actually, even if we try to run their approach, even restricted to classical Hamiltonians, if we try to run their approach at low temperatures, then they reduce to solving an NP-hard optimization problem. So we know that even classically, what they're doing cannot possibly work because they're reducing to some NP-hard optimization problem. Anyway, so now let me state our results. So we are able to solve Hamiltonian learning and polynomial time for any constant temperature beta. So specifically, so for any constant beta, we use polynomial in n and 1/epsilon samples and runtime, and we learn all of the coefficients of the Hamiltonian to accuracy epsilon. So we do have a very bad dependence on beta. So our dependence on this inverse temperature beta is doubly exponential. But nevertheless, we're a polynomial time for any constant beta. And in particular, interesting quantum phenomena arise even for moderate constant values of beta. And so also it is an interesting open question to improve this doubly exponential dependence on beta to singly exponential. And it is known that at least exponential dependence in beta is necessary even classically. So this is basically for the classical version of this problem, which is just learning the weights of a graphical model. Anyway, so now let me discuss the more technical stuff. So let me discuss our algorithm. So our algorithm consists of three high-level steps. So first, we'll make some measurements of the system. We'll measure something called observables, and so this will be the only quantum part of this quantum part of the algorithm. Now, once we've measured these observables, we'll set up a polynomial system to solve for the unknown coefficients, the lambdas with a's. And finally, we'll solve a sum of squares relaxation of the polynomial system to recover the unknown parameters. So, okay, let's begin with the measurement step. So this is pretty simple. So let's say set k prime to be k times 2 to the beta times log 1/epsilon. And now, basically for all possible k prime local Pauli operators a and b, we'll just estimate this quantity trace of a, b rho to some accuracy epsilon using measurements. And this can be done using pretty standard quantum procedures. So this is the only quantum part of the algorithm. So from now on, we can just assume that we're directly given access to these traces up to some small error. So this is all we're doing for the measurements. However, I will take a moment here, and it is important to note that one key difference compared to prior works is that whereas previous works only estimate trace of x rho for x that is k local, we are actually measuring measuring observables that are k prime local for k prime quite a bit larger than k. And it turns out that actually measuring these statistics with higher locality, or kind of higher degree statistics, is crucial to formulating a more tractable optimization problem. And so this is a common theme in many learning problems, even classically, where using higher degree statistics is crucial to formulating a tractable follow-up optimization problem. So next, let me move on to the second part of the algorithm, which is setting up a polynomial system to solve for the coefficients. So, okay, let lambda prime be these unknowns that we'll try to solve for, and let h prime be this matrix of unknowns given by the sum of lambda a prime e sub a. Now we'll try to set up a system of equations to solve for the lambda a primes. So the first attempt at a constraint system, so this is actually called the KKT conditions. But the system that we set up, at least the system that we can try to set up is as follows. So we want to enforce that trace of x, this e to the minus beta h prime y e to the beta h prime rho is equal to trace of y x rho. And so why is this a natural thing to try? Well, at least it is not too hard to see that this condition is at least feasible. So when h prime is equal to h, this equation is satisfied because this equation is satisfied by the cyclicity of the trace. However, this expression in red is not very tractable for efficient or representations or efficiently solving it, because it has this exponential. And to formulate a tractable system, we really want to replace this exponential with a polynomial expression. And so now, okay, so we want to replace this exponential expression with a low degree polynomial. And so it turns out that we can relate this to a natural univariate approximation problem. And roughly this is because if we work in the eigenbases of h prime, then this exponential expression actually ends up becoming just some univariate exponential entry-wise multiplying the entries of y in the eigenbases of H. And this problem kind of reduces to a univariate approximation problem. However, we will need a non-standard, non-trivial notion of univariate polynomial approximation. And specifically, so we need the following notion of an approximation to the exponential. So we need a polynomial that is what we call a flat approximation to the exponential. And we say a polynomial P is a flat approximation to the exponential if it is a good approximation on some bounded interval. And furthermore, outside of this bounded interval, the approximation does not degrade too quickly. So the crux is the second notion, which ensures that basically the polynomial approximation doesn't grow too quickly outside of this bounded interval. And so crucially, many standard notions of approximation fail this second condition and thus are not usable for our purposes. However, so first we show that, okay, we have this notion of flat polynomial approximation, and we show that a flat polynomial approximation suffices to formulate a tractable polynomial system. And now, so to formulate a tractable polynomial system, it remains to construct a flat polynomial approximation. So the construction is so we take the truncated Taylor series and we basically multiply the truncated Taylor series at a bunch of different scales. And okay, we can show that this is a flat polynomial approximation. So that will complete the proof. And so the rough intuition for why this is a flat polynomial approximation is that sort of these different scales kind of amortize the growth of this flat polynomial of this Taylor series so that overall the polynomial approximation ends up being flat. Okay, so finally we formulated a tractable polynomial system, and now we need to solve it. And so what we do is we actually solve a sum of squares relaxation of the polynomial system. So very high level of how sum of squares works and how we can use it to solve this system. So basically it gives us a hierarchy of semi-definite programming relaxations of polynomial systems that are actually solvable efficiently. And so the main thing we need to prove is we need to prove identifiability. That in fact, any solution to the system that we obtain must actually be close to the true parameters. Now, the key thing is that we're actually able to prove identifiability for a solution. And in fact, we're able to prove it in a restricted proof system, namely using only arguments within the sum of squares proof system. And this will mean that our proof actually works for the sum of squares relaxation for free. And so this kind of gives us an algorithm for free because our proof already works for the sum of squares relaxation. So we can just solve the sum of squares relaxation and we're done. So again, this is a very high level proof overview. And so I won't be able to say too much, but perhaps a clear, more concise takeaway for how sum of squares works is the following meme by my co-author Agnesh. Okay, so now let me just conclude with a brief summary. So we give a polynomial time algorithm for Hamiltonian learning at any constant temperature. And in particular, we overcome barriers to learning at low temperatures. And so this gives us a positive result that Hamiltonian learning could be useful for applications. And there are no important computational bottlenecks at low temperatures. And so the two sort of the main techniques are, so first we measure higher degree statistics, and then we leverage a new notion of a flat polynomial approximation to formulate a tractable polynomial system. Then finally, we leverage modern optimization tools, namely the sum of squares hierarchy, to solve it. And I'll conclude my talk there. Thank you.